So what I'm going to talk about is quantum interference. One of the oldest foundational debates in quantum mechanics. It's a double slit experiment. So we're going to be talking about that old chestnut. So I'd like to introduce my collaborators on this work. It was very hard for me to put an institution on most of my collaborators because they're all in transition. So Lorenzo was a postdoc at Chapman, and he will be going to TU Berlin, and these two are on their way to Gdansk, both transitioning from being PhD students to postdocs. Okay, so I don't usually like to start my talks with a big outline slide. So here is the outline. So I'm going to spend a little bit of time talking about what I mean by the question of whether something is classical or not. Now, because of course, there are lots of debates in the literature about whether this phenomenon or that phenomenon is classical or non-classical. And this seems to be a very good way of generating papers, right? So I can write a paper that says, your favorite quantum phenomenon is classical, and then somebody else will write a paper saying, no, it's not, it's non-classical. And then we can have an argument back and forth and publish lots of papers about it, but it's not always clear that that's going to contribute to the debate in a meaningful way. So I'd like to make this, point out some of the difficulties with this question. And then we're going to talk about what is classical about quantum interference in a certain sense. And finally, we'll talk about what's non-classical about it. I have to say that in preparing this talk, I realized I would have less time for that than I expected. So I'm probably in that section just going to tell you what the result is, define what the result is, without going into the technical details of the proof. Okay, so when is a phenomenon classical? Okay, so there are two important things to consider when you're engaging in one of these debates. So the first thing is it depends on the number of assumptions that you make about what you mean by the word classical. Okay, so I can make an argument that everything in the entire world is 100% quantum mechanical if I define classical in the following way. So if I say classical means the laws of Newtonian mechanics plus the laws of classical electromagnetism, plus we can take as an empirical fact the structure of the Rutherford atom. And then we know that the fact that I'm even sitting here and not collapsing into a pile of energy is due to the stability of the atom, which depends on quantum mechanics. Right? So the fact that there's anything at all is quantum mechanical in that sense. And so everything is quantum mechanical. On the other hand, I could make a very, very minimal set of assumptions about what being classical means. I could say this phenomenon has to be explainable using classical probability theory. Okay, so there are obviously interpretations of quantum mechanics which say that probability theory has to be modified. There are also interpretations which say no, it doesn't. We're just using ordinary classical probability theory, like Bohmian mechanics, for example. The probabilities in there are just ordinary classical probabilities. So I can say every quantum phenomenon is explainable in classical probability theory in some sense. And so therefore, nothing is quantum, everything's classical on that definition. Now, of course, there's many things you can do in between those. And generally speaking, I think the most interesting thing to do is to try and reduce the number of assumptions about what you mean by classical while still being able to prove something. Now, we see this with the gold standard of non-classicality, which is really Bell correlations, right? So the number of assumptions you need to prove Bell's theorem is way, way less than, assuming all of classical mechanics, right? And the fewer assumptions you make, the more likely it is that the result you're talking about will have applications in areas like quantum information. because when you're trying to simulate something classically on a computer, you don't really care the exact theory. You don't really care about the exact theory that underlies it. What you care about is, what's the basic structure in terms of locality or efficiency of the simulation. So the fewer assumptions you make, the more likely it is that you're going to get something that's non-classical in a strong sense. Okay, but that's not the only issue. Okay, so the other issue is it depends on what you call the phenomenon, and in the case of these debates, it's often a case of shifting sands, right, in the debate. So let me just give you an example of this. If we take the singlet state and we ask the question, does this state have a local hidden variable model? Well, it depends what you mean, right? So if you are dealing with an experimental setup where you only measure the two qubits in the same basis, then the phenomenon that you get is basically that of the EPR paradox. And we all know that there is a local hidden variable model of that. That is what EPR were pressing towards in their argument. But if we allow ourselves to measure in different bases on the two systems, then we get Bell correlations and we can violate Bell inequalities. Okay, so clearly Bell correlations are non-classical in this sense. But, suppose I wrote a paper claiming that the EPR paradox has a classical explanation. I think I would be correct if I wrote that, but it wouldn't be very interesting for many people. Then you come along and say, but if I measure in different bases, you can't do that. That's interesting, but it doesn't undercut the argument that the EPR paradox has a classical explanation. It's something different that has a non-classical explanation. So this is something that often happens in these kind of debates. Somebody will say, look, here's a phenomenon that's interesting and we think it's non-classical, and they'll list some facts. And then somebody will say, well, actually, that's classical. Here's a model for it. And then the original people will come along and say, well, actually, yeah, but there's this other prediction that you can make with the same setup. But that doesn't undercut the original argument, because that was about those setups, the previous setup. So if you're going to argue about whether something's classical or non-classical, it's important to specify clearly exactly what you mean by the phenomenon, like what is the scope, and also what you mean by classical in a sense. In fact, I would prefer the terms classical and non-classical and genuinely quantum and things like that to be completely expunged from the debate. But I think if I titled the talk something like what is non-huge list of assumptions about quantum interference, then less people will probably be interested in it. I apologize for the light. This happens in my office because there's a sensor that goes off. Hang on a second. Right. Okay. So now let's talk about quantum interference, and this will be the main part of the talk. So I first want to talk about, so we have to specify the phenomenon that we're talking about. Okay. So let me be sort of clear about this. We're going to look at what so the paper on this is still being written at the moment, but in that we call this phenomena that we're talking about the trap phenomena, which stands for traditionally regarded as problematic. Also, the acronym is supposed to indicate that we think it's a trap to think this way. But anyway, most people agree that we can capture the paradoxes of quantum interference with a Mach-Zehnder interferometer. So we are just going to consider the following setup. We have a Mach-Zehnder interferometer with 50-50 beam splitters. Okay, we're not changing the beam splitters to something else. And we have a phase shifter in one of the arms, actually it could be in both of the arms, that we could set to 0 or pi. Actually, in this talk, I won't bother with describing the phase shifter because it's not really important for the main argument. But in the paper, we can have that too. And we also have the possibility of placing a non-destructive detector on one or both of the arms, which just detects whether the particle is in that arm of the interferometer. It's not really that important that it's a non-destructive detector. It could be a destructive one, but I'm going to outline the model for the case for the non-destructive case. Okay, so these are the things that are normally pointed to. So suppose we insert a photon, a single photon on the left-hand path here. If the detector isn't present, and remember, I'm not going to worry about the phase shifter too much, then the photon will always be detected on path L. And this is because you get constructive interference of these two beams on this path and destructive interference on this path. So with 100% probability, you end up on path L. And this is regarded as interference. Well, this is interference, and it's regarded as a wave-like behavior. On the other hand, if the detector is present in one or both of the arms, let's say it's present on the right arm of the interferometer, then it will click with probability 1/2. And regardless of whether it clicks, there will be a probability of the photon being detected on each path of the end at the end. Okay, so we either find out that the particle was on the left path or that the particle was on the right path. In either case, the second beam splitter just gives us 50-50 probability, and this is particle-like behavior, what we would expect to see. All right. So what is traditionally regarded as problematic about this? So different authors will give slightly different accounts of what is problematic. So we have broken this down into 3 different things. The first thing is wave-particle duality. So obviously the photon or whatever is in the interferometer is behaving like a wave when there's no detector there. But we always find when we place a detector in one of the paths, we always find that the particle is on one path or the other, never sort of half on one path and half on the other path. So the particle seems to have both wave and particle-like properties, and which are exhibited depends on how the particle is probed. So that's wave-particle duality. There's also the idea of the observer dependence of reality. So the idea here is that I can choose, it's the observer's choice whether to put a detector on one of the paths or not. So depending on what I choose, the system either manifests as a particle or as a wave. And so it seems like my choice is like affecting the ontology of the system. And then thirdly, there's the idea that there's a failure of explanation in terms of local causes. So basically the idea is that, suppose we put a detector here, then if the particle is going on the left path, it seems to still have to know whether there's a detector here in order to determine whether it's allowed to come out of the right path or not. Okay, so it seems like what's going on over here has to depend on what's going on over there, and of course you could choose whether to put a detector in at the last minute. So you might say, oh, it looks like there's some kind of non-locality, but people also propose explanations like retrocausality and things like that. But the usual kind of causal account in terms of local causes seems to be failing there. Okay, so those are the kinds of things that people say are non-classical about this experiment. Okay, so what is our definition of what we mean by classicality here? Well, first of all, we want the trap phenomena should be reproducible in a model that has none of the 3 implications, right? So the ontology of the system doesn't change. It's the same all the time. It doesn't depend on what choices you make, what the ontology of the system is, and there is a local causal explanation. Okay. technically, if you like technical terms, what we have is a local, non-contextual, psi-epistemic ontological model. Okay, if you don't know what those terms mean, it doesn't matter too much. It also happens to be the case that the model that we present is deterministic, in the sense that the ontology of the system, the state of reality of the system, determines uniquely what the outcome of all measurements is going to be. I don't personally regard that as a necessary requirement for classicality in the sense that we're interested in, but it is nevertheless a feature of the model. Now, the model is essentially just a version of Spekken's toy theory. And in fact, this particular argument I'm going to give in this part of the talk has quite a long history. So in the debate about the nature of the wave function, whether the wave function is a state of reality or a state of knowledge, in Spekken's approach, it's a state of knowledge about some underlying reality. And so basically the wave function is supposed to have a status of something more like a probability distribution than a classical wave. And the first thing that almost everybody says in objection to that is interference, right? So it's, you know, in the Mach-Center interferometer, double slit experiment, etc. Obviously, there's interference going on, and interference requires some kind of wave-like properties. And so therefore, the thing that is the wave-like properties is the wave function. So that must be real. It's the kind of argument that you hear a lot. And in fact, it is correct, as we'll see in our model, that there are wave-like properties, but those wave-like properties simply aren't the quantum state of the system. Now, a lot of this is, well, pretty much all of this is implicit in Spekken's original paper, in which there is an account of how superposition is supposed to work in the theory. However, in that paper, a concrete model of how a specific interference experiment like the Mach-Center interferometer is supposed to work was not given. Okay, so shortly after the publication of that paper, Rob and I came up with basically this idea, and we at that time thought it was so obvious that we never bothered to do anything with it. But in the time since then, you know, people have often asked, how is interference accounted for in this kind of model? So we've decided to do something about it finally. Some of you might have seen a version of this model in a talk that Rob gave at Parameter Institute a few years ago, which is on their recorded seminar archive. All right, so let's just, before we describe our model, we have to talk about the mathematical description in quantum mechanics. And I'm going to give two mathematical descriptions. So the one that you see most often is something like this. So we have the beam splitter transformation, and obviously there are several different beam splitter transformations you can have, but this is the one that we're going to use. So a particle on the left is mapped to right minus left. A particle on the right is mapped to right plus left. Okay, so let's break the experiment up into four time steps. And let's look at what happens when there's no detector. Well, the left state is mapped to right minus left. Since there's no detector here, at T3, you get the same state. I'm going to ignore the phase changes from the mirrors because they're the same on both paths. And then at time 4, you basically get this transformation again, but when you act with this transformation on right minus left, it maps you back to left. So the particle ends up in the state left, and therefore this detector will fire with certainty. When you have a detector, first step is the same, but when you make the measurement, then if the particle, well, basically the measurement, if the particle is found to be on the right, which will happen with probability 1/2. So if this detector clicks, then the state will end up collapsing to R. And otherwise, if it doesn't click, if the detector doesn't click, then you know that the system is on the left, so it collapses to left. So after time step 3, at time step 3, we either have L or R with probability of half each. And then either of those states get mapped to a superposition, equal superpositions of right plus left, which means that at the end, both detectors will have a probability of firing. So very straightforward. But I don't want to use such a simple mathematical description because let's do something more complicated. So I'm going to go to what you might call the field theoretical description, the Fock space description, the second quantized description. Give us various names for it. So I'm now going to treat the left and right degree of freedom as spatial modes rather than states that a particle can be in. Okay, so we're going to construct the Hilbert space in which n, labeled L or R, is the state in which the left-right mode contains n photons. Our Hilbert space will now be the tensor product of a mode description of the left degree of freedom, the left-hand mode, and a mode description of the right mode. Now, the experiments that we're considering here only involve the one photon subspace, so can equivalently be written in the way I did before. But it turns out to be very convenient to rewrite things in the mode description. Now, the reason for doing this is because, first of all, it's more closely related to the structure of the model that we're going to construct. And secondly, we're interested in the notion of locality. And in this description, it becomes clear that the detector, if I place a detector in the right arm, it's a local operation. The operators that describe the detector act on the Hilbert space HR. Okay, so all you do is you sort of translate everything that we had before. So on the one photon subspace, because we don't really care too much about for our purposes, how this acts on the rest of the space. On the one photon subspace, we can just replace the state left with 1 left, 0 right. So 1 photon in the left mode, 0 in the right mode. And then the beam splitter acts like this. And everything's entirely analogous to what we had before. You end up, after 2 beam splitters, with a state in which there's 1 photon on the left and 0 on the right. And so the left-hand detector will click and the right-hand one won't. And then if we include the detector, then we'll end up with a situation at time step 3 where there's either 1 photon on the left and none on the right, or none on the left and 1 on the right. And both of those will get, again, mapped to an equal superposition of a state in which the left detector would click and the one in which the right detector would click. So I hope that's clear. It's like a fairly standard thing when you go from a single particle theory to multi-particle with theory without a fixed number of particles to write this kind of description. Okay, so now let's describe our model. So in our model, a system is going to be one of these modes. So what we're modeling as systems isn't particles, it's modes, okay? So a mode is something that is going to have a state of reality, an ontological state. So a mode gets assigned 2 binary ontic variables. So binary, they're either 0 or 1. So each mode has an occupation number n. So this basically tells us whether there's a particle there or not. And that's in this model going to be either 0 or 1. And each mode also has a phase, phi, which is in some sense a wave-like property. And this phase degree of freedom, you can roughly think of it as the value 0 meaning a phase of 0 and the value 1 meaning a phase of pi. But even though this is a phase degree of freedom, it is not the phase degree of freedom that's the same as the phase degree of freedom that appears in the quantum state necessarily. So a mode has these 2 properties at all times, and that never changes. It isn't sometimes a particle and sometimes a wave. It is at all times a system that has these 2 properties. So we can label the ontic states by n and phi, and then there'll be 4 of them. And this is just here supposed to indicate that, one of these four boxes, one of these four ontic states is the actual property that the system has at any given time. Okay, so that's what's going on in the underlying reality. If we have two modes, as we do in the Mach-Zehnder interferometer, the left path and the right path, then I will draw the ontic state space as a grid like this. So up here, we have the degrees of freedom for the left-hand mode, and along here, we have the degrees of freedom for the right-hand mode. So I'll just label them with the appropriate subscripts. So that's the ontology. That's what's real in this model. Now, we have epistemic states. So again, let's just look at a single mode for now, which could be the left or the right mode. What corresponds to a quantum state? A quantum state gets modeled by a probability distribution over the ontic states. So the quantum states 0 and 1, so this is the state in which there's no photons in the mode, the vacuum state, and this is the state in which there's one photon in the mode. They get modeled by probability distributions, and the blue squares here mean 50% probability in this case, okay? So quite straightforwardly, the quantum state 0 corresponds to, you have a uniform distribution over all of those ontic states which have occupation number 0, and the one state, it's a uniform probability distribution over all of those that have occupation number 1. Now, if we were to look at superposition states of 0 plus 1 photons, so these plus or minus states, they would be the states of definite phase. So here you have the plus corresponds to a phase of 0, and the minus corresponds to a phase of pi. So the plus state is a uniform distribution over those ontic states that have a phase of 0, and the minus state is a uniform distribution over those that have a phase of 1. Okay. Okay, so here I want to emphasize something, and this is one of the reasons for going to this mode description instead of the single particle left versus right description. So an implicit assumption when people are discussing these trap implications of the trap phenomena is that is the following kind of argumentation. So if there is no photon in the mode, so say if we know that the photon is in the right mode so that we know it isn't in the left mode, then it's often implicitly assumed that there is nothing in the left mode. So in particular, there is no degree of freedom that could carry information about whether there was a detector in that mode from that path to the second beam splitter. Okay, this is because there isn't anything there. Now, in our model, the vacuum is actually represented by an epistemic state in which the occupation number is 0, but this phase degree of freedom can have one of two values. So it's possible to use that phase degree of freedom to communicate one bit of information, is there a detector or not, to the second beam splitter. And that's in fact what happens in the model. Now, it's important to emphasize a distinction here, right? So some people will say, oh, you have a ghost particle going along the empty modes. It's not really a ghost particle. It's just that the vacuum is a quantum state and it has substructure, okay? And in a psi-epistemic model, it is completely natural and necessary for the vacuum to be represented by a probability distribution with support on more than one ontic state. Why is that? Well, the very definition of a psi-epistemic state says that you expect non-orthogonal quantum states to have overlapping probability distributions. Now, since we have non-orthogonal quantum states, say the vacuum state and the plus state, they're non-orthogonal. They can't be the same states. They can't be represented by the same probability distribution. So the vacuum state is going to have more than one ontic state if it's going to be able to have an overlap with the plus state, and not be the same probability distribution. You're going to need at least 2 ontic states for that. So it's something that's completely natural and necessary in a psi epistemic interpretation, not something that's sort of unnatural and posited just in an ad hoc way. Okay, so let's talk about single mode measurements. Actually, you can do a occupation number measurement, and you can do a phase measurement. In fact, we won't use the phase measurement at all, so let me not discuss it. So there is an observable that just tells you what the occupation number of a mode is. Okay, so if you're in this state, it tells you it's going to return the value 0 if you're in one of these 2 states, and it's going to return the value 1 if you're in one of these 2 states. This is one of Lorenzo's diagrams. He likes to emphasize the connection to the Pauli stabilizer things, but that's not important here. So he called this a Z measurement, but really it's a measurement of occupation number. And then importantly, after you make a measurement, there'll be a state update rule. So if we do this occupation number measurement, then we'll either find the occupation number to be up here or the occupation number to be down here. Now, if you find that the occupation number is 0, in order to reproduce quantum mechanics, you would expect to end up in the probability distribution that corresponds to the vacuum state. But if you find, if you were in, say, one of these phase states here, and you find out that the occupation number is 0, then if there were no disturbance to the system, then you'd know exactly that you're in this ontic state. But what you really want to happen is that the system should collapse to the vacuum state. So you want to end up in that state. So in order to make that happen, you have to posit a random disturbance to the system. So after making this measurement, with probability half, nothing happens to the system. And with another probability half, this permutation happens to the system. So these 2 get swapped. So the states with the same occupation number, the ontic states with the same occupation number get swapped. So that's the state update rule. Now let's talk about 2 modes. When we have 2 modes, there are going to be states that are product states, like this. And in that case, what happens is that you've just got 2 independent probability distributions, 1 for each system. And now in this case, these blue boxes mean probability 1/4. And those kind of states are going to look something like this, very straightforward. And this is a state, for example, in which we know the occupation number of the first mode is 1 and of the second mode is 0. But you will also have superposition states. And remember, in the mode formalism, a superposition of the 2 paths is going to be represented by an entangled state. And then in this theory, this is a state in which we don't know the occupation number, but we do know that the total occupation number is 1. And we know that the relative phase between the 2 paths is also 1, meaning pi. Okay, if we multiply this by global phase, it would be the same thing. So it's just the relative phase we're talking about here. And then you have an equally weighted probability distribution over these 4 states here. Okay, so if we apply the state update rule to a 2-mode system, so here I'm imagining, so this is describes the left mode and this describes the right mode. We do a measurement on the right mode. Well, all that happens is this state update rule just to the right mode on its own. So the thing is, like, nothing happens to the value of the left mode. This is entirely local. It just affects, the state update rule just affects the ontic state of the right-hand mode. Okay. And then the last ingredient we need is the beam splitter transformation. And this set of equations describes how the degrees of freedom, it's a deterministic transformation, which describes how the degrees of freedom at the output of the beam splitter are related to those at the input. And these symbols here are just addition modulo 2. Okay, so this mess of equations might not seem very intuitive, but diagrammatically, what's happening is just as a permutation where we have 4 swaps of ontic states. And this is a non-local transformation, which is allowed to be because the beam splitter only occurs at points where the 2 modes overlap. Okay. So now let's go back and model and try to model the Mach-Zehnder interferometer in this language. So we have our starting state, then we go through a beam splitter, then we either do or don't do a detector, and then we go through a second beam splitter. So let's see what happens. Okay, so we're going to start in the state 1, 0. So there's a photon in the left arm of the interferometer. So we know the occupation number of the left-hand interferometer is 1. So we're in this upper 2 here. And of the right-hand mode is 0. So we're on the left as well. Then we apply the beam splitter transformation. We look what happens. Well, this one doesn't go anywhere, stays where it is. This one gets mapped down to there by the beam splitter. This one stays where it is, and then this one gets mapped over to here. Okay, so this state goes to this one, which is precisely the state that was representing the superposition. Now, if there's no detector, then between time 2 and time 3, nothing happens. So we're still in the same state. And then if we apply the beam splitter transformation again, well, this transformation is just, as a permutation. If you apply it twice, you get the identity because it just swaps pairs. So this is obviously going to take us back to where we were before. So if you were to measure the occupation number on the left and the right here, you would again find, okay, the left is occupied and the right is not occupied with certainty. So that's straightforward. Now let's suppose that there's a detector on the right-hand arm. Then what's going to happen? So if the system is in one of these 2 ontic states, then you'll find that the particle is on the left, so the detector won't click. If it's in one of these 2, the detector will click because these are where the right arm is occupied. Okay. So in either case, after the measurement, either nothing will happen, or there'll be a random swap that swaps these 2, these 2, these 2, and these 2. So in the case where it was one of these, if we find it on the left, in the case where the particle is on the left, then you'll be in one of these 2 states, but the random swap here will end you up in this state. Okay, so from now on, let me suppose that that's the case. We'll post-select on not finding the mode on the right. But I could equally well see what happened if we did find it on the right, and then you would end up occupying one of these 4. Okay, but if we find it on the left, the detector on the right doesn't click, then we do the beam splitter transformation again. But now we're just in the same state that we were at the beginning. So the same thing will happen. We'll end up in this state, and in this state, the occupation number of both modes is, there's a 50-50% probability of the 2 modes being occupied. If one is occupied, the other one isn't. So we will find those detectors clicking with 50-50 probability. Okay, I believe I'm running out of time soon. What do I have, about 10 minutes, Howard? Probably. Yeah, you're muted, but I will. Okay, let me continue. So I've just given the most basic Mach-Zehnder interferometer here, but you can obviously reproduce things which are essentially just the Mach-Zehnder interferometer with slight modifications. So the Englert-Weibman bomb tester works the same way. The bomb acts just like the detector. And the Wheeler's delayed choice experiment, obviously it doesn't matter here how late you make the choice of whether to put detectors in or whether to put the second beam splitter in even. And we can extend the model. We can include more systems, ancillary systems. We can extend the model, and we can reproduce things like, for example, the delayed choice quantum eraser. And there's no funny business regarding causality going on there in this model. And that's not the end of it, because of course there's a whole list of things which are like this, and many of them that are claimed to be non-classical can be reproduced in a similar way. Okay, so if that's classical in the sense that in the precise sense that I'm talking about here, what is non-classical about quantum interference experiments? So if you like, we found our EPR experiment, right, which has a classical explanation. What's the analog of the Bell correlations, which shows that there is some non-classicality here? Well, you have to be a bit careful here, because obviously, if I allow myself enough flexibility, so if I allow myself non-50-50 beam splitters, arbitrary phases, then I can essentially do any experiment on a qubit with a Mach-Zehnder interferometer. And we know that there are no-go theorems for qubits. So Speckens contextuality, for instance, works for a qubit. So obviously we can, with the Mach-Zehnder interferometer, get non-classical phenomenon. And the only question is, what's the minimum thing? The thing that's sort of most closely related to what we think of as being characteristic of quantum interference that is non-classical. So what we considered is the trade-off between which-way information and visibility of the interference in a Mach-Zehnder interferometer. So this has been studied by many people, but in 1996, Englert showed a well-known inequality, which is that the square of the visibility plus the square of a distinguishability measure between the two paths, I'll discuss what these are in more detail in a bit, has to satisfy this inequality here. Actually, the way he did this was, he made a model for the detector which collects the partial which-way information in terms of quantum mechanics. And when that detector happens to start in a pure state in his model, then you actually get equality here. So for mixed state detectors, you get the inequality. And for a pure state detector, it's possible to get any values of visibility and distinguishability that satisfy this equality. So what's our result here? So we've already really considered the cases where visibility is 1 and distinguishability is 0. That's where you don't have a detector at all. And the case where visibility is 0 and distinguishability is 1, that's the case where you have a perfect detector like we were modeling. So what we prove is we consider formally an ontological model for the detector. So I think you could also transfer this over to the photon, but the way we do it now is we try to say, okay, let's take this detector and see if we can create a classical model for that. If we require a preparation non-contextual model in Rob Speckens' sense, then you can only reproduce the quantum predictions for a pure state detector in these two cases that we've already considered, in the two cases that are covered by the model that I just presented. No other values of visibility and distinguishability are allowed. So it's not possible to extend the model to cover cases of partial which-way information. So let me just give a brief overview of the setup. I'm not going to talk about the proof at all. So suppose that when so we have a detector. So P now stands for the photon degree of freedom and D for the detector system. So suppose that if the photon is on the left path, that the detector ends up in some state A, and if it's on the right path, it ends up in some state B. By changing the global phases of A and B, which don't matter, we can always make the inner product of A and B real. So let's suppose it's given by some parameter cosine theta. And then, in that case, you can always find some orthonormal basis for the subspace spanned by A and B, such that A and B have these representations in that basis. So we then have to describe what the detector interaction is. Without loss of generality, you can assume that the state in which the detector is ready to perform a measurement is this zero state, in this basis that we defined. And then the measurement interaction is just this. It just does this, basically. It's a partial detection. So if A and B are orthogonal, then we have perfect which way, we're going to have perfect which way information, but otherwise we won't be able to distinguish A and B with certainty, so we'll get only partial which way information. Okay, so the definitions that are used is that the visibility is, so if you have perfect interference, then the particle will either come out in the left or the right arm. So we take the modulus of the difference between the two, and that's the visibility, analogous to the fringe visibility in a double slit experiment. And as our measure of distinguishability, we take the trace distance, which is operationally well-motivated distance between states, and it's linearly related to the probability of success of determining whether a system is prepared in A or B if you don't know which. So for pure states, it actually has this expression. And I can also define, actually, I'm not sure I'm going to need this, but I can define this mixed state here, which is a 50-50 mixture of A and B. Okay, so now the Englert inequality happens because Englert equality rather happens basically from Pythagoras theorem, because on the Bloch sphere you can show that D is half the distance between these two, and V is the distance between the maximally mixed state and rho. And then Pythagoras theorem tells you that you get the Englert equality. So I'm just going to say what our result is again. So if we want to try and find a Speckens non-contextual model, what that consists of is we have a set of states of reality, ontic states. For every quantum state, you assign a probability distribution to it. And importantly, the non-contextual part, preparation non-contextual part, is that this probability distribution is only allowed to depend on the quantum state rho, not on how it was prepared. And similarly, for every POVM element, you have a conditional probability of getting that outcome given the state of reality. And we say the model reproduces the quantum predictions if, upon averaging over what you don't know about the ontic state, you reproduce the quantum probabilities. And then, so here's the result again. Such a model exists for this detector if and only if V equals 1 and D equals 0, or V equals 0 and D equals 1. And I'm pretty much out of time, so let me just say one more thing and then conclude. So it's interesting to consider the case of mixed states, and we're still sort of in the middle of doing this. But the conjecture which we've sort of virtually proved is that if you start allowing the initial photon state to be mixed, or the detector state to be mixed, then a non-contextual model would give you this inequality without the squares. And so therefore, if you had values of V and D in your experiment violating this inequality, then that would be a proof of contextuality. Next steps, finish that proof. We would like to robustify this proof so that it can be tested experimentally without making any assumptions that, say, quantum theory is true or that our predictions are exactly right. Then I have to persuade a friendly quantum optics experimentalist to do the experiment before obtaining prizes and glory. Okay. Conclusions. If you allow yourself enough flexibility, you can reproduce any qubit experiment with a Mach-Zehnder interferometer. And since there are Speckens contextuality proofs for a qubit, it's guaranteed that you will find some set of Mach-Zehnder setups that demonstrate contextuality. But what is the minimal set of such setups? Is it the ones that have been traditionally regarded as problematic in the sense of, the interference paradoxes? Well, no, we can reproduce those. But the which way visibility trade-off that we have in quantum mechanics specifically cannot be reproduced. Okay, so thank you for your attention. I will leave it there.
So we've pretty much gone through most of the question time, and we're running a bit late. So maybe if there's one particularly brief and insightful question. Well, I didn't mean to put too much pressure. Yes. Someone from online, I believe, has a question.
Oh, hi.
Hi. So I would like, the ontic variables you use are only depend on the past and not on the future.
Yes.
And on the other hand, we've heard talks such as Hardy's last talk, which emphasizes symmetry. So why not allow the ontic variables to depend on future settings? Is that, would they be non-ontic in this case?
No, I wouldn't say that. I mean, like the goal of this model is not to try and reproduce all of quantum mechanics. It's what we're trying to do here is make a separation or be a bit more rigorous about the separation between what we consider to be a non-classical phenomenon and what we don't, right? So as you know, I am not opposed to models with retrocausality where things depend on the future, but there is a question about where is that necessary? Is it necessary, for example, to have that in order to reproduce, say, a delayed choice experiment, okay? And some people would have said, well, yes, it is. Obviously, what the particle was doing in the past must depend on this choice of whether you put the beam splitter in the future. But this model shows, no, that doesn't have to be the case. There's a natural model in which that doesn't occur. So it's sort of a question of, there are non-classical things in nature, and obviously we have to do something. We have to modify our models in some way to account for those non-classical features. And one thing you might do is allow retrocausality, but it's a question of determining where's the dividing line between what actually requires that and what doesn't. You see what I mean?
Thanks.
All right. Well, let's thank Matthew for a very nice talk, and also all of the speakers in the second afternoon session.
Thank you.